Hey folks, I'm Jolly from Camp Adventures, and in this video I wanted to cover a extremely popular free wiring diagram that goes round online a lot. Okay, the wiring diagram in question is what you see on the screen now. So this is Greg Virgoe's electrical wiring diagram. I know he's done a few, but I see this diagram come up a hell of a lot in Facebook groups. It's been raised in my Facebook group, and yeah, I see it come up a lot. So what I wanted to do in this video is raise awareness of like the safety and improvements, well, like the safety issues, the things that need to be updated in regards to UK and EU regulations, and improvements that need to be made to it. I see it a lot, like I say, and it's hard for me to sort of swoop in and correct what people are asking or correct the wiring diagram to each individual person. So the reason why I'm doing this video is for that, is to give you that awareness. So what this video is not, is I don't want anyone to think I'm here just to slate Greg. It's not that at all. I personally have a lot of respect for Greg Virgoe for what he's done in the community, and obviously on YouTube he's helped a lot of people out. I'm focusing on this wiring diagram, and I'm not going to sit here and just rip it apart. What I need to do is update it for safety, for regulations, and give improvements to it because of the amount of people that use it. And installing it as it is, exactly as it is, doesn't mean it's not going to work. It is going to work, and it does work. It will function. However, just because something works doesn't mean it's safe, doesn't mean it's done in the right way, and doesn't mean it's done to regulations. Okay? Regulations can be seen as a very boring topic, and I mean it is. If you sit and read the regs, it's extremely boring, but they're there for a reason. Okay, and we must follow those regulations to ensure the system is safe and it's functional. So what I'm going to do in this video is I'm going to go through all the points on this wiring diagram you see in front of you and go through the what's wrong. So the safety compliance based on BS 7671 UK regulations, which is if you follow the UK regs and you're in the EU, so anywhere outside the UK and the EU, then you'll be fine. Okay. There's nothing different with the EU compared to the UK. There's a few slight changes, but if you follow UK regs, you'll be fine in the EU. There are quite a few improvements that need to be made, not always specific to safety issues, but there are improvements that could create issues in the future, or if not done correctly, could create safety issues, if that makes sense. Okay. And I've just got some additional info as well. So what I'm going to do is show you, not that one, I'm going to show you this one. So this wiring diagram here, I'm just going to remove my video so you can see it properly. So this wiring diagram is Greg Virgoe's exact one. However, I've noted some points on it so you can see all the points that need to be updated, okay, for safety or any other reason. So in green, so you've got 1, 2, 3, 4, 5, and 6 in green. They are what's wrong, and I'm going to go through why it's wrong as well, okay? Oh, there's number 7, sorry, number 7 lurking over here. And then the orange ones, they are improvements. So I'm going to give you like best practice upgrades for 1, 2, 3, and 4. Okay. Now, all the information I'm going to give you is available in a wiring diagram. So what I've done, I'm just going to bring myself back. Hello. What I've done is I've created an updated version of this wiring diagram. And it not only updates exactly what you see here, what it also does, because I know not everyone's got 275 watt solar panels, the Renogy DC-DC MPPT isn't stated if it's 30 or 50. I believe on the video, Greg refers to it as a 30, but it's not stated on this wiring diagram. And the other one is the inverter. Not many people use the 1000 watt, it's more the 2000, 3000. So the updated wiring diagram I've done gives you the option to select your cable and fuse sizes and adapt the installation, whether you've got the 30 or 50 amp DC-DC MPPT, whether you've got the 1000, 2000 or 3000 watt Renogy inverter. Okay, I'll go a bit more in detail on that updated and I'll show you the diagram that I've got available, and it'll be available to download in the description underneath this video, but I'll go into that after. I'm just going to go through all these points. So what I'm going to do, I'm just going to hide me for a minute because number one is lurking behind my head. So all the points I'm going to bring up are based on the exact diagram you see in front of you now. Okay. So again, the green ones are basically the main ones really. What's wrong, what needs updating. So number one here, this is the inverter fuse is undersized. So the diagram shows a 100 amp fuse for a 1000 watt inverter. So at full load with the 1000 watt inverter, it's unlikely you'll ever put full load through it because it won't like it. It's likely going to alarm and it'll push it to its limit. However, you must size the system to the max load because obviously that's what the system can carry. So at full load, the 1000 watt inverter is about 93 amps. Now you need to convert the watts to amps to get to that figure. So it's 1000 watts divided by the system voltage, which is 12, divided by the efficiency of the inverter. Now as a generic calculation rule, you use 0.9, which is 90%. Most inverters now are more than 90% efficient, but some are about 90, 91%. So that's why I use the generic 0.9. So the reason why it's 0.9 is because you need to put more power in to get the 1000 watts out of the inverter. Because the way that electricity converts, you're going to get some energy loss. It's normally by heat. So obviously things get hot when the electricity converts. That's what's happening. So it's converting from DC to AC. It's going through electronics to get to it. That's your inefficiency. So it's about 0.9% efficient, which gives you 93 amps. Okay. To size a fuse, you need to use the 1.25 fuse rule. So a fuse is sized 25%, like 25% more of the load. So it's 93 times 1.25, which gives you 117, so 117 amps. Now there's not a fuse that's 117 amps, so you round up to the next one, which is either 125 or 150 amp, depending on what fuse you're going to use. So that 1.25 rule ensures that if the inverter is pushed to the max to 93 amps, that the fuse isn't running at max capacity, because it could nuisance blow or it could just run really hot for a long time, which can degrade the fuse and the cabling as well. So the 1.25 gives you like a 25% buffer to ensure the fuse is okay. The reason why the 100 amp fuse isn't sufficient is it's because it's too close to the working current and therefore can run hot or nuisance blow. Okay, that's what I was getting at. So the 100 amp in regards to safety will protect the circuit. However, it needs to be about 125 at least. So if you're installing a 2000 or 3000 watt inverter, obviously the fuse is going to be different. Okay. The other one to note here, where number one is the cable size. Now 25 mil will come up okay on a voltage drop calculator. However, the recommended cable size for a 1000 watt inverter is 35 mil. The reason for that is once the higher the load, the more voltage drop there could be. Okay, using 35 mil will ensure that it keeps that voltage drop to the minimum. Okay, so you make the most of the power. I'm going to bring myself back. Hello. So let me just put my light on so you can see my face. Number two is missing inverter casing bond. Okay, that's a really important one. So that's to do with like the AC system as well as the DC, but that's part of UK regulations. So inverters typically have a metal casing, which this one does. So it must be bonded to the chassis for safety. So all sort of class 1 appliances and components. Class 1 means it needs an earth for safety reasons, and class 1 are typically metal casings. So that's why it needs an earth for safety. So if for any reason there's a short inside the unit and the live touches the casing's metal, it's conductive, it could become live. An earth needs to be there for safety reasons. Okay, so you must earth that inverter, the Renogy inverter, from the casing to the chassis to its own chassis point. That chassis earth mustn't be connected onto any other chassis earth point. Okay, it must be onto its own point. And the minimum recommended cable is 4mm. So that's green, yellow, AC stranded cable. Okay, so just to recap on number 2, if you're installing any inverter, but specific to the Renogy inverters, run a 4mm earth from the inverter to the chassis. Number 3 is a leisure battery has no battery isolator, which is a requirement. Okay, you need to be able to isolate those batteries. At the moment, the way it's wired, you'd need multiple isolators to isolate the power of the batteries. Okay, so leisure batteries, they need a proper means of isolation from the rest of the system. A battery isolator is required for this. Okay, but the battery wiring layout must be designed so the isolator actually isolates everything it should. So when you turn that isolator off, what it should do is turn off all the power from the battery to the rest of your system. That's there for many reasons. It's there for maintenance. So if you need to work on your system, you just turn a switch. There's no power from the battery. Obviously, you need to also make sure there's no solar power via the isolator and no AC. They're separate at the moment, but obviously you need to check that. You isolate the batteries if you ever need to remove them, if for like winter use, if you don't use the van, and for safety reasons, if you ever need to isolate the batteries from the system. And in regards to the wiring, I'll go through that in the next point. So where the improvements are, like 1, 2, and 3, I'll cover that in a bit. But basically, the way the wiring is, with multiple positives going to both positive battery posts, you can't just have one isolator. Okay, you need multiple isolators, which is not the best way of doing it, should I say. Next, we'll move on to the AC system. So this is where the majority of the issues are. So number 4 is on the mains hookup. Okay, so there's no RCD protection on the hookup mains inlet. The hookup mains inlet, if you don't know, so that's where you connect your campervan AC system to the campsite or your house. So like the mains, so the mains connects the mains the mains to your van, if that makes sense. You just have like a hookup lead and plug them in. So that's how that works. So regulations state that the first connection for the mains hookup cable, so this blue one, must go to a double pole isolator. So you can't connect, as this is shown here, you can't go from the hookup to a socket, because a socket's not an isolator, it's a socket. So you can't isolate that cable. So what the isolator is there to do, you turn it off and it isolates the AC from your entire system. But what you also must ensure is that you have RCD protection. So the best way to do that is you've got your hookup point, which is this one here. You wire that into an RCD or an RCBO. Okay, so that's what you do. Because an RCD or RCBO are double pole isolators. They switch off the live and the neutral at the same time. And they monitor it as well. So you'll have an RCD with an MCB or an RCBO. And what that's doing, that's protecting from overcurrent and short circuit current, and also giving you RCD protection. So that's what that needs. and that is UK wiring regulations. Number 5 is, again, no RCD protection on the sockets or the final circuits. So number 5 is here. So what's happening there is the inverter's converting DC to AC. That black part is the 3-pin plug, and you're going from there to wire to additional 230-volt sockets, which is absolutely fine. So obviously the inverter has a socket built in, but if you want sockets elsewhere in your van, you'll wire a socket circuit and then connect it to your inverter, which is absolutely fine. What's not fine is that there's no RCD. So that's specific to this system. Now, you don't need an RCD if you're plugging in class 2 appliances. What class 2 means is it's double insulated. What double insulated means is generally so class 2 appliance doesn't need an earth for safety. So typically they only have a live and a neutral. So they'll have a plug, and whether you've took one apart or you've ever noticed before, sometimes it's thin flat cable. There won't be an earth. Now it doesn't mean it's unsafe. What that means is it's class 2. So instead of it being metal, it's got like plastic casing or coating. So it's double insulated from the live parts. Okay, so even if there's a fault inside the unit, you won't get a shock because it's inside that insulated double layer. So that's where you don't need an RCD. You must install an RCD, and this is for UK wiring regulations, the BS 7671. If you're wiring socket final circuits, which is what we have here, so you're physically wiring a cable to a socket, whether it's one or multiple, and or you're plugging in class 1 appliances. So class 1 appliances are appliances that require an earth for safety. They're typically metal, so that's like a kettle, a toaster, induction hobs the same. So they might not be metal on top, but they might have a metal casing underneath. They're the typical ones for camper vans anyway. So they require an earth for safety because they're metal. So because of that, you must have an RCD to protect you, okay? The RCD is not there to protect the circuit. It's to basically prevent you from dying, okay? So put it as morbid as that. That's exactly what it is. It stops you from getting a fatal shock. So it's checking that for like earth leakage. So if there's a fault with the appliance, the actual power from the live could end up going down the earth and finding an alternate path. Now, if you're holding that appliance and it's metal and the live touches the case, you could be that path of electricity. The RCD will sense an imbalance. So the power that's going out through the live doesn't come back in through the neutral. It's now going through you. It will sense that imbalance and switch off. Okay, so it stops you from having a fatal shock, which is why it needs an RCD. Now, I'm sorry if that's a bit confusing for anyone, but I'm just going to make it a little bit more confusing. Typical inverters, there's not many in the market that have it built in. Victron do, and the Renogy Inverter Charger Pro do. But Renogy inverters, if we stick to this diagram, you can install an RCD, but it won't work because the output of an inverter is what's known as floating. So it's floating from earth. It doesn't actually have an earth. Now, that doesn't mean it's unsafe. What makes that scenario unsafe is the scenario it's installed into. When you install it in a camper van, you start installing circuits to sockets and you're plugging in class 1 appliances. That's when these inverters become unsafe. So what you need to do is you need to introduce a neutral to earth bond, which turns the power from floating into an earthed system like your house, which then means an RCD will work. Okay. I'm sorry if that's mega confusing, but that is the biggest issue with this wiring diagram. And it's not just like Greg from this wiring diagram that don't know or don't include that bond and RCD protection. I see it constantly with energy inverters. Unless you have that knowledge already, you can buy an inverter, plug something in, and you're none the wiser, okay? So I'm hoping to give you a bit of knowledge now, and if you have that inverter, to take action to make sure it's safe, okay? At the very end, again, I'll show you that wiring diagram and give you a bit more understanding. So sticking with 5 for a moment, the solution to this, if you're wiring socket circuits, is you wire from the inverter into a consumer unit, AC consumer unit, and you either wire it through an RCBO, which is an RCD and an MCB combined. If you've got one circuit, use an RCBO, then your socket circuits, okay? Otherwise, you go into an RCD, then MCBs, and feed your final circuits. But you must introduce that neutral to earth bond, which is in the wiring diagram. Okay, that's important. Number 6, which is, I've just put it there, but what it's referring to is the entire AC system. So the AC system main earth is missing. Okay, it's not labelled on this diagram. Again, this is UK BS7671. I'm losing track of my mouth. Wiring regulations. Okay. When you install an AC system, you must install an earth bond, which is your main bond. So when you go from the mains hookup into a consumer unit, you've got a consumer unit in your mains. You may have one at your inverter output as well. What you'll do is you'll link those earth bus bars together, and you'll send a main earth cable, which is 4mm or bigger, green yellow stranded AC earth cable, from the consumer unit earth to your chassis. It must go to the chassis to its own chassis point, so it's not doubled up with like the DC negative ground or the inverter casing bond. It must go to its own one. The other important thing is it must be at least 300mm away from any other chassis bond or ground. Okay, that might seem a bit silly, seeing as obviously the chassis is metal. Surely it doesn't matter how far you are away, they're still going to conduct, and the fault path and stuff's going to go through. That's right. What the distance is doing is, if there's any DC fault or like stray current that ends up on the chassis, sometimes it can get into the AC earthing system. You don't want that. What happens when DC current goes into an AC system is it can blind an RCD or an RCBO. What that means is, if there's ever a fault on the system and there's DC current in the AC system blinding the RCD won't see the fault. Okay, so that is quite a big thing. All right. So you need to make sure what I would do is, like, your DC negative ground, if you need it, and your inverter casing, bond those to as close as you can. The main earth, just send it somewhere else. It doesn't matter how long that cable is, it just doesn't. So you can send it to like the back of your van or something, just put it as far away. So at least you just reduce that risk of DC stray current getting onto your AC system. So yeah, again, I appreciate there's a lot to take in with the AC side of things, but it's extremely important, not only for functionality, but for safety. That's the big one. Okay. The last one on, safety and improvements is number 7 over here. And what that one is, that's the solar fuse. So which is this here. It's called an MC4 inline fuse. Now, a misconception is that you must install a fuse for solar panels. Okay? You don't. You only need to install a fuse if there's a requirement for it based on your solar panels, from what you've installed. The only time it must be installed is if you're in Australia or New Zealand and you're following their regulations, because they request it. Doesn't matter if it needs it or not, you must install a solar fuse. Okay? UK and EU, you don't. I wouldn't advise installing one anyway, because the biggest fail point in a solar system is the MC4 connections, because generally they're placed on the roof. They are protected from weather, so they're IP rated, so they won't let weather in, like rain or anything, and they are protected from UV. However, they can be on the van for years at a time, and I've seen them go brittle. I've seen them fail. They can get moisture as well. So they are if something's going to fail, it's typically the MC4 connector, and you've probably seen it. They just literally push together. It's just a push fit connection. Okay, so why is this fuse an issue, and why is it not required? Now, if you wire your panels in series, so here they're wired in parallel, so all the positives are together and all the negatives are together. If you wire them in series, it's also known as like daisy chain. So you'll have the positive to the negative, negative to the positive, positive to the negative. Got that right? So it goes like a chain. Whereas parallel, I like to call it spider wiring. So all the positives together, all the negatives together. In series, the voltage increases, but the amps stay the same. So if you wire in series, you do not need a fuse. Okay, the amps won't get high enough through the solar panels to cause any damage or any problems. In parallel, because when you connect two panels or more in parallel, the amps adds up, so you add each panel together. So the amps increases, okay? When the amps increase, that's when you cause it, there could be an issue. So if there's ever a fault, there could be an issue on the system. So every solar panel will have a max series fuse rating, it will say on it. Typically, lower wattage, like anything under up to about 200 watts, is about 15 amps. Okay, so that's the max series solar fuse, 15 amps. If the combined amps of the solar panels is less than 15 amps, you don't need a fuse. If it's more than 15 amps, you need to put a fuse on each panel. Because what that means, if there's ever a fault, that current could flow in the system. If it flows to a panel, if like, let's say 20 amps flows to a panel that's rated at 15 amps, it's going to damage the panel. Okay, it could just make it fail. It could cause it to catch fire or burn. That's why you have to have a fuse. Okay, what I'll do, I'll explain it here, try and give you a bit of a visual to understand how you do that. So what you're looking at is the ISC, which is the short circuit current. Every solar panel will have a spec, and every solar panel will specify its ISC. These panels here, the ISC is 8.88. Because they're parallel, you times it by 2, so you add 8.88 to 8.88, which gives you 17.76 amps. Okay. Now these panels, they have a max series fuse rating of 15 amps. So obviously the total amps, which is what you'd get on this cable here, because you've got two panels combined. Okay, what you're getting is 17.76. It's higher than the max fuse rating of each panel. So if the fault current ever flows, like the max, which is nearly 18 amps, if it does flow to any one of those panels, the fuse will blow and protect the panel. That's how it works. Okay, that's why you need fuses and why you don't need fuses. Adding a fuse just adds a fail point in your system and a resistance point, and it's completely pointless if you don't need it. So depending on what panels you have, if you've got a single panel or they're in series, you don't fuse it, because series, the current stays the same, so it never exceeds the max of each panel. In parallel, or if it's series parallel, that's a bit different, then you may need a fuse, so you need to do the calculations. So in regards to safety, that like the major safety concerns, that's 1 to 7, the green ones, so they're sort of covered. What I'm going to move on to now is the improvements, so like the best practice upgrades is what I call it. Okay, that's what we'll do now. So there's 1 to 4. So number 1 is to do with battery balancing and cable lengths. And this could sort of be a safety concern, but it's more practicality really. So first of all, what I mean by battery balancing is it's making sure when you've got 2 batteries that they're balanced in regards to their voltage and capacity. What you don't want is one battery that's like 80% capacity and charged and the other one 50%, because there's going to be a difference in their internal resistances. And what happens is current will flow down the path of least resistance. Okay, so if your batteries are out of sync, you could end up having a lot more power going down one of the cables than another cable. So it could give more charge to one battery and like completely disregard the other one until that's charged and then charge the other one. And it's once they start going out of balance, you'll notice it creep more and more. Okay, that can cause an issue with the cables as well. The other thing with balance is each battery, typically 12 volts, they're made up of normally 4 cells. This is like for lithium, there'll be like 4 cells in it. Each cell needs to be the same voltage as well. Okay, you normally get that when you monitor through the apps, you'll notice cell voltages. That's another thing with balancing, but that's like internal battery balancing. What I'm talking about now is separate battery balancing. So what needs to happen in regards to the cable lengths is when you link 2 batteries together in parallel. So what you'll do is you'll put a positive between the positive posts, negative between the negative posts, and then if you're going out, anything that's like the parallel battery connections, the cables must be exactly the same length, not slightly different, but exactly the same. Okay, if they're slightly different, there'll be different resistances in the cable. So longer the cable, the more resistance, if you think of it that way. So a short cable, the current can flow easily because there's no resistance. A 100-meter cable, there's going to be a lot of resistance for it to get through. Okay, now when resistance increases through one cable, the current will flow down the other cable with, well, path of least resistance. So it could flow down the other one, okay, causing an imbalance in the batteries. It can cause hot spots in the cable if you don't size it properly. So instead of the current being mixed between the batteries, it could go to one. And if you've not sized the cables properly, you can get hot spots and heat. So that's a big one. The way to overcome that is I'll get into in a minute is changing the configuration of the wiring for these batteries, which is number 3. Okay. So number 2 is limit cables on battery terminals. Now, I see it often, daily, probably in a lot of Facebook groups, in my group, and just online in general, that a lot of people just put all the positives to the positive and all the negatives to the negative. And it does work, but it can cause a lot of problems in time. Okay. A battery, I mean, they are AGM on this drawing. I mean, they're still pricey, obviously still got price to them. But if I focus on lithium, it's probably the most valuable part of a van because it gives you power, but it's also valuable expense-wise, isn't it? So the last thing you want to fail is your battery. Wiring all the cables to the battery posts can put a lot of strain on that battery post. Not only from the amount of cables, obviously the strain on it, but a cable connection is where heat is going to be caused. So if you don't do a good connection, like if you don't crimp the lug brilliantly, or the connections of the lugs onto the battery post aren't brilliant, but they're also going to cause resistance anyway because it's metal on metal. So if there's heat going to be generated, it's going to be right at the battery terminal. If you get excess heat, it can melt the battery terminal or damage the internals of the battery, okay, which means potentially new battery. So you don't want to be doing that. That's the main problem, really. The other one you can find is the bolts for the battery might not be very big. So if you put more lugs on, there's less of a solid connection into the battery. Okay, it's more likely to come loose and work loose because a van vibrates. Bolts and screws can easily come loose if not checked regularly. Okay, so it can actually come loose, and you can't over tighten battery terminals because you can crack it as well. The best rule of thumb for that is a maximum of 2 cables per post. That's the best rule of thumb. In some instances, you might need 3 on one post, but the rule of thumb is 2. The best solution for this is what I'll go on to next, which is number 3. So yeah, point 3 is to use a busbar or a distribution box. So what a busbar is it's basically just a solid bar of metal where cables connect to. A distribution box is exactly the same, except there's fuses built in. Okay, so a busbar is just where you connect the cables. A distribution box is busbars with fuses built into it. Why do I recommend that? So what it means is instead of sending everything to the batteries, so it's all on the terminals, you have a central busbar or distribution box, and you send everything to those points. So what you do in this example here, you'd have a central busbar or distribution box, and you'd connect the blade fuse box to it, you'd connect the inverter to it, you connect the DC-DC MPPT to it, and you'd also run a cable out to your batteries. So it's like a central hub for all your main battery connections. That all goes to it. And the main benefits of doing that is it enables isolation. So point number 1 before we did, yeah, the green one behind my head, I think, yes, behind my head. It means then, because you've got one cable from the busbar distribution box to your batteries, you can have an isolator for your battery. So when you turn that isolator off, it literally removes the battery power from your entire electrical system just from switching it once. It means you've only got one isolator. You want to reduce the amount of cable connections because that's where the heat resistance and fail points are going to be. So reduce all those as much as you can. It keeps things lovely and tidy. It really does. So it's much easier to connect to because they're all, laid out nicely. It keeps it all neat and tidy. I know that's not always in the main forefront of people's minds when they do systems, but it also means if there's ever a fault or an issue, or you need to upgrade or change, it's all neat and tidy. Switch the isolator off, remove or add something to the busbar distribution box, switch it back on, job done. Whereas when they're all connected like this, you have to undo the bolt, everything comes off. If it's in a tight space, which batteries usually are, that's an utter ball ache, and it is. I've had to do it on installs, and it's a pain in the arse, it really is. And it reduces a lot of potential resistance in the system. So where the bus bars are designed to carry a certain amount of current, you'll design the bus bar for your system. With an inverter, you probably need a big one or a big distribution box. When I say big, I mean like higher rated to take the current. They're designed to take a lot of current. So when you connect your cables to it, you're getting a better connection overall, which means it's more reliable, and just do it. It's loads better. And the final one, number 4, is here. So that's to do with the blade fuse box. Now, this is just an improvement and something to note when you're installing a 12-volt blade fuse box. What's here is perfectly fine in regards to the cable and the fuse. There's no issue there, okay? But what that limits you to is about 20 amps through the blade fuse box. Again, that's fine if that's, the limit of circuits and appliances you're connecting to that 12-volt fuse box. The reason I say 20 amps is because there's a 25 amp fuse, and you don't want to push it. You want the fuse to be 25% higher than the max rating. So it's about 20 amps roughly. Now, what I always recommend, if you're installing a blade fuse box, it's typically the 12-way one. You don't see many that are 6-way, many people using. It's near enough the same cost as a 12-way. You might as well just put a 12-way in. They're rated to 100 amps. What I would do personally is install the cable and the fuse that can carry the max power the 12-volt fuse board is rated to. Why you would do that is you've never got to worry then about adding or changing anything in your 12-volt fuse box. A lot of vans, if you have your first van, you install it all, do your electrical system, then go and use it. There's always improvements or changes. There just is. It's just the nature of the beast, really. There's always like things to change. You could end up wanting to install more circuits or changing what you've got to bigger like load demands. What that means is you've got the cable and the fuse in, done. So it's a little bit more expense when you're installing it and you think, oh, it's a bit overkill, but it's there if you need more power. If, for example, you're in this system, 20 amps is your limit, but you want to install something, I don't know, you would want to put a diesel heater in, or you want to add a fridge, and it puts you up to like 30 amps load, then you then need to change the cable and the fuse. The fuse is obviously not going to like it, it's going to blow. But to uprate that fuse, you potentially need to uprate the cable as well. So what I would do is put 16 mil and 80 amp fuse or something and just be done. The reason I say 80 amp is because even though it's rated to 100 amps, the blade fuse box, you'll probably never push more than 80 through any one time. That's a lot of power. And that covers all the improvements. The one thing I will raise, that when I put this exact image and everything I've sort of gone through in my Facebook group, and a lot of people picking up saying there's no leisure negative chassis bond, but it's not really I'll say chassis bond, it's a ground point from the negative system, so the black negative. Now, I will cover that now, that's a part that is correct in this system, is you don't need a negative chassis ground point in this system, okay? A lot of people suggested it. The system doesn't require it. And actually adding another negative chassis bond can introduce what's called grounding loops, okay? So what I'm getting at here is most people believe that this is your negative DC cable, the black. You need one from there going down and then grounding, onto your chassis. That's a typical setup. You only need the negative ground if your system requires it, okay? It's not a regulation, it's not a requirement unless your system requires it. The scenarios where your system needs it is if you've got an inverter, because you need to bond it to the chassis. That bond for your inverter could also have DC fault current or DC stray current. So you must have a negative chassis ground, okay? So yes, this system does need one. However, it already has one here at the van starter battery. So every vehicle will have a chassis ground from the negative starter battery post down onto the chassis. So there already is one. The reason why this system doesn't need one is because introducing two negative chassis grounds in one system causes what's called grounding loops. And you can draw it with your finger or pencil of a wiring diagram. It means you can make a loop, okay? So what it would mean is if you've got a ground here and a ground here, you could literally go up and then back down along the chassis, up, back down along the chassis, and it creates a loop. So that's where the issue is. But why is a grounding loop a problem? So grounding loops, they can cause issues known as noise. And that's not noise like a drill noise, like sound. It's electrical noise. It's sometimes interference, and it can actually affect your components because there's like electrical noise in the system. It can cause strange faults with components, and it can actually interfere with fuse behavior. So the fault current can actually flow down a different path. So if you've got multiple grounds, or even just 2 or more, the actual fault current can flow down a different path and either delay or not cause a fuse to blow, which can actually be quite serious. Okay, now I'm talking worst case now. In some systems, grounding loops won't ever cause a problem, whereas in some systems they will cause a lot of problems. But I always try and do worst case down generic approach, just avoid them. Because then if you ever change your system or you ever do anything else or you ever giving advice to somebody else, just don't do it. Okay. I'm not going to go into too much detail in this video because I appreciate your brain's probably already fried from the information I've given. I'll do another video or something, or I'm going to actually do a blog post on grounding loops to cover it in a bit more detail. But be very mindful that if you're installing this one, the DC-DC MPPT, that if you put a negative grounding like here, that the starter battery negative is connected all to one point in negatives to your leisure system, so you will get a ground loop. The other one, which I haven't commented on, is a lot of cable sizes. So I can't confirm the diagram's cable sizes without knowing the cable lengths and the installation method. Okay, so to size a cable, you need to know the load, so the amount of amps that's going to flow through it, the length of the cable in meters, the voltage, which we presume is 12 volt, an installation method, which can cause other factors for cable sizing. But it's mainly the length, that's what I'm getting at. So that's why I've not commented on any cable sizes. The key takeaway really is to, number one, read your manuals. You wouldn't believe the amount of people that don't even look at the manual. It's just basically something to start a fire. They just chuck it on the fire rather than actually reading it. Please read the manuals because the manufacturers do specify cable and fuse ratings. The other one is use designs that are built by qualified and experienced people and they comply with proper standards and real world experience. Okay. Don't rely on a diagram that's just because it's popular online and everybody uses it and the person who designed it is popular and got a good face. Okay. I'm not saying that that person isn't qualified to give the advice or to design it. I'm just saying look into it a bit. All right. There are people out there like myself who are qualified electrical engineers. I've been doing it for 20 plus years now. I've been in the campervan and off-grid game with electrics for 10 years. So I've sort of done it. I've got the experience. I know the regulations. And there are other people that do as well. Okay. So just do a bit of digging, do a bit of research into whoever you're getting your designs from. The next step is to use the diagram that I've designed. Okay. So it's based on this diagram you see here, obviously, and it goes a lot more in depth. So I'm going to show you that now. So here we go. The link will take you to here. This is my website. If you're on the website, if you just click wiring diagrams there, it brings you to this same page. And if you scroll down, at the moment, because I've just uploaded it, the Greg Virgoe wiring diagram updated version is there. Obviously, it's very, very obvious. There it is. Now, this page might be slightly different when you come here. I've not long set it up, so you can see there's an issue with some weird text there. I don't know why that's there. It needs updating and tweaking a bit, but there is other wiring diagrams in here, a lot of Renogy stuff, and they've got about 30 or 40 more diagrams to actually upload into here. Popular systems, so people have got access to them. But if you go to the Greg Virgoe wiring diagram, I've currently got it on sale. So if I click on it, it takes you to the product. So because this is a full wiring diagram system, like schematic, you can use it to install your own and like build your own. The price is it's currently 49, but I've got it at 29 at the moment. I've got a sale on it. You know, it replaces the Greg Virgoe one with a proper wiring diagram. Currently, you get it for 29. Okay, which is insane, really, if I'm honest. So, but the main thing, I just want you to be safe. I want you to do it properly. I want you to find proper guidance and practices, and yeah, do it proper. So there we are. You know where to go. Like I say, links in the description again below. You know where to find me, and have a lovely day, and I'll hopefully speak to you soon.